In this unit, we're going to be learning about arithmetic, geometric, and general sequences. So let's go over a definition of a sequence. A sequence is a set of numbers, shapes, letters, etc. that are in a distinct or recognizable pattern. So you might want to just highlight that. We're going to focus on numbers for this unit. So I've given you 3 examples of some sequences, 1, 3, 5, 7 being the first one. You can probably predict that the next number in the sequence is going to be 9, and then the number after that is going to be 11, so on and so forth, because you can probably tell that we just have to add 2 to get the next number. 12, 24, 48, the next number is going to be 96 because we have to multiply by 2 every time. The last one is a little bit trickier, 3 over 4, 5 over 9, 7 over 16. The next number in the pattern is going to be 9 over 25. See if you can figure that one out. All right, so sequences are discrete functions, which we sort of briefly touched on back in Unit 3. And remember, discrete functions means that they have gaps or holes in the domain and range. All right, whereas continuous functions, if you remember also back from Unit 3 when we first were introduced to this definition, they have no gaps or holes, so they're curves, lines, okay. And basically, their domain and range are the set or a smaller set of real numbers. When we think about the domain and range of sequences, the domain would be the set or subset of natural numbers, so starting with 1. The range would be the actual terms of the sequence. So in the example, let's say 1, 3, 5, 7, just those first 4 terms, the domain would be 1, 2, 3, 4, because there are 4 terms. Okay, first term, second term, third term, fourth term. The range would be the terms themselves, so 1, 3, 5, 7. Some notes about conventions. The first term in a sequence is referred to as T1, the second term T2, so on and so forth. So the little subscript tells us what term number we're talking about. The nth term would be referred to as T subscript n. If you notice the punctuation in the sequence, the terms are separated by commas. And right over here, the ... called an ellipsis tells us that the pattern continues indefinitely or forever. So as I said at the beginning, a sequence could be arithmetic, geometric, or neither. An arithmetic sequence has terms that are separated by a common difference. So that means you have to add the same number every time to get the next term. So in the example 5, 7, 9, 11, you would have to add 2 every time to get the next term. So that 2 is your constant difference. The domain for this sequence would be, again, there are 4 terms, so 1, 2, 3, 4. And the range would be the term numbers themselves, so 5, 7, 9, 11. In 20, 16, 12, 8, you would subtract 4 to get the next number. Okay, so that's the constant difference. The domain for this sequence, because you see the little ellipsis there, that means that we will have a domain as the set of all natural numbers. And the range, well, we're going to come back to this later after we figure out the formula. A geometric sequence, on the other hand, has terms that are separated by a common ratio, meaning you have to multiply by a number to get the next term. So over here, 2, 6, 18, 54. Multiply by 3 every time. That will be your common ratio. Okay. The domain, again, there are 4 terms, so 1, 2, 3, 4. For the range, the terms themselves are 2, 6, 18, and 54. And last example here on this page, 80, 40, 20, 10. You would have to multiply by half every time to get these terms. So constant ratio is half. The domain, again, because of the ellipsis, we're going to have the set of natural numbers for our domain. And for the range, we'll come back to it after we go over some formulas for the general term. So let's go over how we can find the formula for these sequences. Sometimes a pattern can lead to a general rule, and this rule is called the general term for the nth term. So in both arithmetic and geometric sequences, the value of a term depends on the value of n. So if we were to talk about it in terms of functions, the value of a term would be the dependent variable, which is denoted as t subscript n. And the value of n, the term number, would be the independent variable. So let's go over the example for an arithmetic sequence. So here we have the term numbers going across the top. Here we have the terms themselves going across the bottom. Now we already know that for an arithmetic sequence, in order to get to the next term, we have to keep adding the common difference d. So if the first term we start with is a, then the next term we would add d to a, so then we get a plus d. That's the second term. The third term is going to be another d added on. So if we were to simplify, that would be a plus 2d's. And then the fourth term, we would add another d. So then that we get a plus 3d right there. And if you continue the pattern, what do you see? This 3 and this 2, you just have to subtract 1. This 4 and this 3, you just have to subtract 1. So by the time we get to the nth term, we're just going to have to subtract 1, and that's how many multiples of d we would have added on to a. So we get the formula a plus n minus 1d. And in fact, that is the general term for an arithmetic sequence. All right, arithmetic sequences, if you think about it, the terms keep increasing by a constant number, so that means that we can represent them using a linear function. All right, for a geometric sequence now, again, we start with the initial term of a. In order to get to the next term, we need to multiply by some constant value r. So the second term is ar. To get to the next term, the third term, we would multiply by another r. If we simplify, that would be ar squared. To get to the fourth term, we multiply by another r, and we end up with ar cubed. So as you can see, if we continue the pattern, we're going to end up with ar to the power of n minus 1. Because again, in order to go from the term number to the power on, or the exponent on r, we just have to subtract 1. And that gives us the general term of the geometric sequence. If you recall way back from Unit 4, if we have an exponent that is a variable, then we end up with an exponential function. All right, so you might want to just put a little box around this or something so that you have your... Oh, my pen's running out. Better. All right, so very important key concepts. Little stars next to those. All right, let's go over some different question types that you'll encounter. The first one is what is, or find, the nth term. So 10th term, 20th term, millionth term. This is asking you to determine the value of t subscript n. So in this first example, the perimeter of an equilateral triangle can be represented using the equation p equals 3n. So p in this case could be t sub n, where n represents the side length. Determine t30 and t50. Basically, this is asking you to find the perimeter of an equilateral triangle with side length 30, and this is asking you to find the perimeter of an equilateral triangle with side length 50. From the top of the page, we know that if we have an exponent of 1 on n, then we are going to end up with a linear function, right? And that linear function is the same as an arithmetic sequence. So let's find T30. All we need to do is plug in 30 for n, 90. T50, plug in 50 for n, 150. In the next example, find the first three terms in the sequence described by Tn equals 3 to the exponent n. So again, from the top half of the page, you know that if the variable is an exponent, then we have an exponential function, and therefore we must have a geometric sequence. So first three terms, T1, 3 to the power of 1, so 3. This is really the same as A, okay? Second term, 3 squared, 9. Third term, 3 cubed, 27. So 3, 9, 27, first three terms in the sequence. Now this last example, find the 15th term in the sequence f of n equals 2n squared minus 1. F of n is just function notation, same thing as writing t subscript n. If you notice, this time there's an exponent of 2 on the variable base. This is a quadratic relation. A quadratic relation is not arithmetic nor geometric. And sometimes we can have sequences like that. That's okay. So that doesn't stop us from finding the 15th term. All we need to do is sub in 15 for n. So 2, 15 squared minus 1, 2, 225 minus 1. And that gives us 449 as the 15th term. All right, moving on to the top of page 3. The second question type, to determine the general term of a sequence. And you have to be given at least 2 terms in order to do this. So find the general term of means determine the formula. So determine either the arithmetic sequence general formula or the geometric sequence general formula, or possibly a totally different formula, neither arithmetic nor geometric. And we'll go over an example like that. First off, if you're given 2 terms in an arithmetic sequence, first of all, you want to determine the common difference d between the terms. If you're given the terms that are consecutive, then that's really easy to do. All you need to do is subtract the previous term from the next term, so t2 minus t1 or t3 minus t2, that will give you the common difference. But what if you're not given 2 terms that are next to each other, but there are some terms in between them? So let's say you're given tc and th, then in order to find the common difference d, you are going to subtract those 2 terms, th minus tc, and divide by the number of terms in between them. So for example, if you know the 4th term and the 11th term, in order to find the common difference, you're going to take the 11th term, subtract the 4th term, and you're going to divide by 11 minus 4. Once you've done that, you can use the common difference and one of the given terms to determine the initial value a. So let's go over this example. Given the 3rd term as 17 and the 8th term as 37. This means that the 3rd term being 17 and then the 8th term being 37, there are 1, 2, 3, 4, 5 skips in between those terms. So you've added d 5 times. So take t8, subtract t3, divide by 8 minus 3, or 5 skips. So 37 minus 17 divided by 5. That gives us 20 over 5, which is 4. And I'm out of time, so go on to the next video. Alright, my apologies for not being able to finish up the example in the previous video, but here we go. So we found the common difference to be 4, and now we just need to use the general term of the arithmetic sequence formula. I'll plug in 17 and 3 for n, and the common difference, 4, we just found that out. So this 17 and that 3 comes from the 3rd term being 17. And this common difference 4, well, we just found that out. So 17 is equal to a plus 2 times 4, 8. So a is equal to 17 minus 8, which is 9 if I'm not mistaken. And then Now we want to plug in our a and d values, leave tn and n as variables. Simplify, and you should get tn is equal to 4n plus 5. The next example, if you're given two terms in a geometric sequence, you want to determine the common ratio r between the terms. If you are given consecutive terms, then really simple, divide the second term by the first term or the third term by the second term. Again, if you are given two terms that are separated, then this is going to require a little bit more work. R is going to equal, now subtract h minus c, because that will tell us the number of steps or skips in between those terms, and take that number and you're going to root the ratio of th divided by tc. So what I mean by that is, if you have, let's say, the second term and the fifth term and you want to find the common ratio r, then you're going to take the cube root, because that's how many skips there are between 2 and 5, 2, 3, 4, 5. And then you're going to divide t5 by t2. Once you have the common ratio, just use that and one of the given terms to determine the initial value a. So when you use the general formula, Tn equals AR to the power of n minus 1, you will have just found Tn and n, or sorry, you would have been given that information, and you would have just found your value of R. So you can just rearrange the equation to get A. And that equation is A equals Tn over R to the power of n minus 1. So in this example, the third term is 24, the seventh term is 3 over 2 in a geometric sequence. Determine the common ratio and A. So R is going to equal 7 minus 3, take that number, take the root of 7, t7 divided by t3. So you want to take the fourth root of 3 over 2 divided by 24. Now 3 over 2 divided by 24, that is the same as 1 over 16. The fourth root of 1 over 16, half. So that's your common ratio R. And once you have that, you can find A by doing Tn over R to the power of n minus 1. So I'll take 24 for Tn, and R I just found is half. 3 minus 1. This 24 and this 3 comes from the fact that the third term is 24. And so you get 24 divided by a quarter, which equals 96 as your initial term. All right, last example, and this is tricky because you're given two terms in a general sequence that is not arithmetic or geometric, so you can't use the formulas at the top of the page. So instead, you just have to try to look for the pattern that gives you the term number based on, or sorry, the term Tn based on its term number n. So in this example from the first page, this is n equals 1, n equals 2. Oh, you know what? Sorry, I didn't like that, so I'm going to rewrite it. So n at the top, 1, 2, 3. Okay, first term, second term, third term. Try to look for the pattern that gives you the numbers in the numerator, that gives you the numbers in the denominator. The numerator follows the pattern of an arithmetic sequence, so I'm going to use Tn equals A plus n minus 1d, plug in my 3 for A, and plug in 2 for the common difference, and Tn equals 2n plus 1 for the numerator. The denominator are just whole numbers squared, 4, 9, 16. If you see the pattern, it's going to be n plus 1 squared, the term number plus 1 squared. And now put them together, numerator divided by denominator, and here is our general formula. If you turn back to page 1 for a minute, we left the range for these two examples blank, and the reason for that was because of the ellipsis telling us that the pattern continues forever. So it wouldn't be enough to just state 20, 16, 12, 8 for the range, or 80, 40, 20, 10 for this range. We have to actually come up with the formula and state the range that way. So for the first example, this is an arithmetic sequence. Come up with the general term. Tn equals A plus n minus 1d. Plug in everything that you know. First term is 20, n minus 1, negative 4. And when you simplify this, you should get negative 4n plus 24. So that's going to be your range. And n belongs to the set of natural numbers because we can't have such things as negative term numbers. We can't have, 1.5 term. All right, and complete the same thing for the geometric sequence here, 80, 40, 20, 10. So Tn equals AR to the power of n minus 1. The first term is 80. The ratio is half to the power of n minus 1. That's really all you need to do for this example. So you can just plug that in for the range. And again, write that n has to belong to the set of natural numbers. And you're done. So turn back to page 4. We're going to go over the last question type number 3. All right, in this last question type, what term is or does blank, so some number, belong to the sequence given? So in this question, you need to determine the value of n. If n is not a natural number, it does not belong to the sequence, meaning the term, rather, does not belong to the sequence. All right, remember, for all sequences, n has to be a natural number, so it can't be a decimal value, can't be a fraction, can't be a negative. All right, so let's go over this example. Given the sequence Tn equals 3n minus 2, that's an arithmetic sequence, determine what term is 775. So in this example, we are given Tn as 775, and we need to figure out what the value of n would be. So really simple, just plug in 775 for Tn, rearrange, isolate to solve for n, and you should get 259 as n, so therefore 775 is the 259th term in this sequence. For part B, whether or not 1023 belongs to the sequence. So again, we need to remember n must be a natural number. So n must belong to the set of natural numbers. All right, so do the same thing as in part A. Sub in 1023 for Tn and solve for n. Now divide both sides by 3, and we end up getting that n is equal to approximately 341.67. So as soon as we see that n belongs to the set of real numbers, not the natural numbers, we can say, therefore, no, 1023 does not belong to the sequence. So those are the 3 general question types. And now for the rest of the page, you can do the examples on your own and just pause the video. Every time you've done the example, just press play again and the full solution will show up so that you can see what it is. And in tomorrow's class, we will go over this very briefly, and the rest of the time will be for you to work on the assigned work. All right, so go ahead with the practice questions. Okay, so here's the full solution to number 1. Tn is equal to 3 times negative 4 to the power of n minus 1. For question number 2, you can assume that the first term is 2000, and if you figure out the general term as 4n plus 1996, then plug in 6,388 into Tn and solve for n. You should get a whole number for n. So since that whole number belongs to a set of natural numbers, yes, the year 6,388 will be a leap year. Okay, last example, you should get Tn equals negative 4n plus 3 for the general term, and no, negative 200 does not belong.